most of the solutions for. And so this is, it starts on section 2.8, and we'll take 2.9 too, but when we talk about conditional probability, this is actually, it's important for a couple of different reasons. So with conditional probability, if something has happened, we want the probability of another thing happening if there's a relationship. And let me just do the Venn diagram again. If this is A and this is B, where these areas represent the likelihood or probability of something happening, and this is the entire event space here. And sometimes they use omega to represent that. And we look at the intersectional area there, that is A intersect B. Then when we take a look at the probability of, say, A, given that B occurs, is really going to be the probability of A intersect B over the probability of B. In the book, what they'll do, oftentimes they'll just have P of A, and then it will be B over P of B. You all follow me on this? I'm just going through something we talked about a while ago. And they try to make you think in terms of areas being proportional to the likelihood of the event occurring. That's the only thing with this Venn diagram stuff, in my opinion. There may be more to this. So if I take a look at something, and this should make sense to everybody, I'm going to say that this is the probability density function for something. Doesn't matter what it is. So this is f of x. And x can have a mean value. It doesn't really matter what this is. Now, I know that the base, if that is a probability density function, the integral of f of x dx from minus infinity to infinity must be 1. That has to be. I don't think anybody disagrees with that. Agreed? So now, what happens if we talk about the probability of, say, x being less than, I'm just going to pick some x1, given that it's less than m. So I'm going to state it this way. The probability of random variable x being less than or equal to x1, given, and the way he does it in the book, he'll put a comma right after this, given that x is less than m. So now, what you have to do is think in terms of area. All right, what would be the probability of x less than x1? And there is an assumption here. We're assuming x1 is less than or equal to m. I better put it up here. So I'm saying x1 less than or equal to m. Otherwise, this would be the probability of x being, now think about this, if the event occurred, if m occurred, and I want the probability, it means it's less than that point. What's the probability? It's greater than that point, it's 0. Do you all follow me in this class? It has to be. So when you do it this, the way I think of this, and the book does it about the same way, but he uses the cumulative distribution function here, instead of just writing it down this way. When I take a look at this, and I think about these Venn diagrams, first I take a look at the probability of x, random variable x, less than m. Well, that would be the integral from minus infinity to m of f of x dx. I don't think anybody's going to argue with that. Do you agree with that, class? Now, when I take a look at the probability here of x, of it being, I should say, of the random variable being less than or equal to x1, and I'll put it this way, and this has to be, well, wait a second. Yeah, that's it. random variable less than or equal to x1 given m, well, that's the probability of x less than x1 given random variable x less than m over the integral, or really over the probability of random variable x being less than m. And here, and I'm going to say something about this in a second, and I hope I'm trying to make sure I say this in a way that's correct. This is, if you were looking at the slides, this is on page 98 and 99. In your text. But what I'm going to do is now I'm going to take a look at the probability. I think I put it down. So this is the probability of x less than m, and the probability of x, random variable x less than x1 itself would be equal to the integral of f of x dx from 0 to x1. Then if you come over here and write this the way he does it, and what this is actually, I think, I better put it over here. This is a distribution function in his book. So he's going to do it. He's going to say now this is the cumulative distribution function of f of x, random variable x less than small x, given m occurred. And what he's going to do is say that it's going to be based on an integral from minus infinity to x of f of x given m dx. So he's saying that this f of x given m, and I'm going to try really hard to explain this in a way that makes sense. This is going to be the density function that's going to be augmented from the original density function, say, is known. It could be Gaussian or whatever. Now, if we have that it's less than m, there's one thing that happens, and this is the key to this whole thing. It means if I take the integral from minus infinity, all right, to m of f of x given m dx, I must get 1. That should be clear to you. If m occurred, y'all with me on this? So, I mean, it means that x is less than m, somewhere down here. If that happens and we have a conditional density function, probability density function of f of x given m, it means if you integrate that density function to the point m, that's over the total possible range. It has to be 1. And he'll say that in his book. Should make sense. So now, he's going to come down here and say, the only thing I've done here is I want this density function. I'm trying to formulate it the way he did. We don't know the density function yet. We're going to in 1 second. This is a cumulative distribution function. So if we knew this distribution and we integrated it from minus infinity to x, that would be the probability, all right, of that event occurring. But it's given this one occurs. Now this is a numerical value. Do you agree with that? If m is stated like 5, 10, whatever, this is a single value. It's not a function of x, correct, class? So now when I take the derivative of f of x given m with respect to x, now I get my f of x comma, or f of x given m. If you look at that, what that really is going to be the derivative of this, which is just going to be f of x right here. This m means nothing at that point, and then it's divided by this, which is going to be integral of minus infinity to m of f of x. But, you know, when you take a derivative of this, the only thing that's a function of x is the top one. Now, when you evaluate this, basically when you do this from minus infinity to x, you're evaluating only this kernel of integration at the point x, which is the same thing as evaluating f of x, just the density function. And this is what it boils down to. I'm not saying it's the way I'd like to. This entire thing right here, the probability density function of x given m, is really going to be, I'll put it here, you see some problems with it. I think it'll make sense. This is really just going to be equal to f of x, this is the density function, given m, is the original f of x, and it's just normalized, I call it that, by the integral of simply f of x dx from minus infinity to m. That's a constant, and that constant value would be less than m. Now, I think you can see it this way. So if I have a density function like so, versus x, and I say the event m occurred, all right? One thing I know about this conditional density function, if I integrate the conditional density function to m, I have to get 1. Do y'all follow me on that? If I say m has occurred, in other words, x is less than or equal to m, that would be the definition of that, then this density function, the actual conditional density function, has to be 1 if I integrate it over the entire range it's allowed to be. Now what that really means is this. You take the original density function, and remember it has to be 1 when you go and do that integration to m. Well, this is integrated the density function to m. The only possibility is this density function up there has to be the original f of x, but it's just scaled by that. Does this make sense? The way I'm saying, I'm really trying, but I don't know if it's really just taking the original density function, and now what you're doing is scaling it so the entire area, it'll be a proportional area, but it's all scaled from minus infinity to that point m, and that's the only thing. So I've thought about ways to do this, and that's about as good as I can get for this one. So then, when you take a look at this, in his book he says, well, what happens to the mean? And this is, again, he shows this on page 100 and 101 in the book, and you can take a look at the associated notes. But I think the easiest way to see this is just doing some examples. So let's see. And then we'll talk about the expected value. Now we're going to get into the next chapter 2, and this is when you get density functions that are functions of both x and y if you have 2 random variables. But for now, I think I'm going to just try to explain this thing in a way that will make a little more sense. And we'll do problems. So if you think about it now, remember that f of x given m is really just the original f of x, the probability density function, divided by something that scales it proportionally from minus infinity to m. M is given as a curve of f of x dx. That's that. Now when we take the expected value of x, well, that technically is the integral from minus infinity to infinity of x, or whatever the function is. If we wanted the expected value of x squared, we put x squared. If we had the expected value of any other function, that could represent like a sine of x, or cosine of x, or cosine squared. Y'all with me? Whatever's inside that bracket goes here. And then you take the actual f of x, and I should say this is the expected value of x given m, but it's kind of implied, and then f of x given m dx. Now, if you look at this, by itself it doesn't mean much until you see it applied, until you see an example. So you can take this right here, and remember, this is a constant. So you can simply replace that by some c. That's just a constant. You with me? So I can come over here and I can say what this really is just going to be the integral. Now technically it goes from minus infinity to infinity, but if it's conditional, this becomes m because it can't be larger than that value based on the definition he's using of the conditional probability. So here it's going to be the integral from minus infinity to m of x right here times this, which is f of x, right? And then it's got to scale by this, by the integral from minus infinity to m of f of x dx. That's just a constant. And this is dx.
Couldn't you cancel those two?
Which ones?
So if you separate x and f of x.
These two, no.
Oh,
this is an integration.
Yeah,
X f of x, it's multiplying. This isn't like x constant. I can't pull it up. So for this one right here, you can see it's basically, this scales something. This looks like the normal expected value, but the range of integration is limited. So now, the best way to see this is apply it to something. And in his book, he has some things to say about the Gaussian, what it means to the Gaussian derivation of this. But pretty good, he's got a couple of good ones. If you take a look at example, and I'm going to need you to help me with your calculators on this. If you look at exercise 2-8.1, and I'm going to do this, and we'll do the next one. But I remember when I went through this course, it was a senior level course when I took it at Penn State years and years ago. We used a book called Larson and Schubert, but the thing that I found most helpful to understand how these problems work is visualization of something proportional to areas. That's the way it always worked for me for most of the problems. Just, mathematical formulas, unless you get an idea what's going on, it's hard to appreciate. So for exercise 2-8.1, I'll tell you what I'll do. I'll hand my book to the trusted reader, the cantor. All right, go ahead.
2-8.1.
Yeah,
A Gaussian random voltage having zero mean and a standard deviation of 100 volts.
Now that's standard deviation. That's a lot. 100 volts. Go ahead.
Is connected to a series with, or connected in series with a 50 ohm resistor and an ideal diode. And find the mean value of the resulting current using the concept of conditional probability.
All right. Here's the one thing about this. You're used to having voltage as a constant. Either you have voltages with switches, which are just like a DC voltage and a switch closes, or you have voltages at constant frequency. But in the real world, most of the time when you're expressing a voltage, especially something due to the natural environment, it's a statistical, not a time-varying description. So for here, they're saying this voltage source, whatever's causing it, has got a statistical definition of it. The mean is zero. That sounds like something related to the natural environment. It probably sounds like something where you have photodiodes in some way, but it doesn't matter, creating a voltage. Then you have a mean of, or a standard deviation of 100 volts. And what he wants is this. He wants the average current that flows there. That's what he's after. Now, if you think about this, current, by definition, is equal to V divided by R, right? But here we have something that's a little different. That diode is the thing that flips the switch. So I'm just going to draw this out. Let's assume there's some statistical point in time space where the voltage is going to be symmetric for some period of time. Say this is the voltage V of t, and I want to plot the current on top of it, I of t. And let's say I of t is positive this way. Well, you know it will flow in this direction as long as it's a plus to minus voltage. But if it tries to flow the other way, it gets zipped. Correct, class? That's the only point I'm making. That's the only thing a diode does, is limit the direction of current. So here on a positive cycle, the current would trace it, be proportional to the negative cycle 0. Positive and then 0. That's the point I was going to make here. So, if that's the case, if we wanted to figure out the actual value of that current, now think about this. So I want the expected value, right, of the current, which is, and I'll put this as I bar. Expected value of the voltage over the resistance, but there's a qualifier. Voltage has to be positive, right? So this is going to be 1 over R, and it's the expected value of the voltage given that V would be greater than or equal to 0. Y'all follow me on this, class? Just think about it. Does that make sense?
Yeah.
Do you remember this problem, Kenny? Or not?
I didn't look at it.
I mean, this is one of the classic problems they show you with conditional probability. I mean, it really is this type of problem. They'll find other ways to do it, where you have something that makes everything, I just call it, takes AC, goes to DC, or takes something and makes it only a one-way type of action. We know the mean of the voltage is 0. The mean of this is not going to be 0. So what do I really want to get? I only care about what? 1 over R. I want the expected value of the positive voltage, just V, the expected value of V, given that V is greater than 0. So now I have to go, and I'll do it right here. My original voltage, just watch this. So the actual original Gaussian description of the voltage, this is the density function for the voltage, would be 1 over the square root of 2 pi, and then sigma v, exp to the minus v squared over 2 sigma v squared. That would be the original density function, correct? Just take a moment, make sure you see this. Now if I take a look at that, I'm going to graph this too. So here's the original density function. This would be f of V versus V. But now I say for my event, the thing has got to be an upper quadrant, right? I only care about the density function assuming it's positive, correct, class? And this is what that proportionality comes in. So my f of V, given that V greater than 0, think about this. This is 1 over the square root of 2 pi sigma V times exp to the minus V squared over 2 sigma V squared. Right? That was the original density function. I erased that, put over there. Now I have to divide that, right, by the associated area of the given event occurring, right? So now I have to divide this by, really, because it's 0, I mean, it doesn't matter if I go from minus infinity to 0 to infinity. Now I have to divide that by the integral from, technically from 0 to infinity. So this is the event, this is the area associated with the positive event. Does this make sense to everybody, class? It has to, what you're gonna divide by is the area associated with the event occurring, the given event occurring. So this goes from 0 to infinity of 1 over square root of 2 pi times sigma v exp to the minus v squared over 2 sigma v squared dx. Now, I did this for a reason, that's why I say this. This is a Gaussian distribution, right? What's the area of f of x or f of v under from minus infinity to infinity is 1. What is it from minus infinity or from 0 to infinity?
1/2.
1/2, right? Follow me? So I can replace that by 1/2. And if you look at this, and I'll need your help for this. So this becomes 1/2. Or I can multiply the top part by 2, can't I? So that's the actual distribution. And this is only for v greater than or equal to 0. Now I can do this. We'll do it right over here. But I'll need your help. I don't think I can get this on my own. This is one of these numerical intervals, I think. So what I need is this. I want this right here. I did this last night on math class. I was playing with these problems, and I don't have solutions for these things, but I have answers. So when I look at this I bar, I know it's 1 over 50 because that's the value of the resistance. Now, when I look at the expected value of V for that distribution, I have to take an integral from 0 to infinity. I want to make sure you're seeing what I'm doing. You with me? The expected value would be the function V times the density function integrated over the range. You with me on that, everyone? I see people writing, which I'm glad, because this is a good problem. And it really does showcase stuff. So it goes from 0 to infinity, the value of V. Now it has to be the augmented density function over there. So now it's going to be 2 over the square root of 2 pi. Those could come out in front. Sigma V is 100 volts, right? Y'all with me on this class? Now it's times exp of minus V squared over 2, but that's sigma V squared or 10 to the 4th.
Wouldn't v squared be 0 anyway?
Huh?
Is it?
What are you talking about? V squared is the integration.
Oh, yeah, you're right. It's not the random variable.
V bars.
Yeah.
So this is 2 times 10 to the 4th, right? dV. And that should do it. So the actual I bar, this is the integral I need to help you with. So I'll take all these constants out in front. So I get 1 over 50. And then I got times 100. And then I have really, I can put this as the square root of 2 over pi. And then I have to evaluate this integration, which is the integral, can somebody do this for me? From 0 to infinity of v exp to the minus v squared over 2 times 10 to the 4th dV. And can you give me? I want to make sure you can do this on the calculator. This integral is the key.
I got 1.59577.
I think that's the answer, isn't it? 591.
59577.
Yes.
And that, in fact, I think is the solution, or the answer.
Yeah, that's right.
15958.
Now, this problem is, this type of a problem is something you see over and over again later on. I think you're going to see it over and over again. Has anybody here had calm at all? When you have these kind of things, he won't talk about a voltage. I mean, he may talk about a signal. A lot of times they don't even define it as a voltage, but something like this where the statistical component becomes important. All right, now what's the next one? Is there another part to that question?
No, there's a question underneath it.
Yeah, let's do that one too. Let me erase this. But this is, is the next one related to this or not?
Meantime, it's a mean time to failure.
Oh, okay. I didn't do that one, but why don't we? Because this is also something where they get, I think this is the exponential, right? Okay, the mean time to failure only depends on the distance or the time between events. Well, let's see what I'm talking about. Most recent events. Okay. Go ahead.
A traveling wave tube has a mean time to failure of 4 years. Given that the TWT, I guess that's traveling
wave tube.
has survived for 4 years, find the conditional probability that it will fail between 4 and 6.
So this is the problem I wanted to talk about Friday. So he's saying he wants the probability of a failure, let's say the events of failure, between t greater than 4, less than 6 years, given that t is greater than 4. It survived 4 years. Y'all with me? I'm going to put this up here. So here's the goofy thing. Here's time. And if the event starts here, normally you think, well, the only thing you've got is you're going to have this thing is the actual density function, f of t for failure, time to failure, is 1 over t bar, and it's going to be exp to the minus t over t bar, and that's the density function associated with failure. So the probability of failure, if you integrate this from 0 to infinity, is 1. Trust me on that. So he says it doesn't fail up to this point, 4 years. Right? It made it that far. What's the likelihood it goes from 4 to 6? This is the best way to do these problems, all right? Now, I mean, what's the probability it fails between 4 and 6? Isn't that how it's stated?
Yeah.
All right, the thing you know is you're going to have to take the original density function. The way I just say is shift it to this point to start it. Because the only thing that matters is that they say if it made it this far, the only thing that matters is the distance between here and here. You take this original distribution, literally, instead of starting it at 0, you start at 4 years and just do it that way. Yep. Now, I'm telling you, if we did it the way he does it, where he says that now what you do is get f of t given t greater than 4. You don't have to write this down. He's going to take the original density function, f of t, as such, and then he's going to augment the thing where he's going to divide this by the area from 0 to 4 of f of t dt. But the easiest way, and you'll see this, in my opinion, if you listen to me, take this functional form that you have here. That would be the density function. Then you would go ahead and you would have to integrate that density function between 4 and 6. Here's the easiest way. Take the original density function, the exponential decay, and just move it over here so the height is 1. And then, if you want the time to failure, in this blue region right here, you take the original density function and integrate it between here and here. And that's over a distance of simply 2. Y'all with me? It's the easiest. So the probability of failure, given that the thing survived t greater than 4 years, has nothing to do with 4 or 6 or 8. It has to do with the distance between that point and where you want the failure. So it's just the integral from really 0 to 2. I've taken the skew out of this one. You all with me? And it would be 1 over t bar e to the minus t over t bar dt, and that is going to be what? Well, it's going to be simply e or it's actually 1 minus e to the minus 2 over 4, so it's 1 minus e to the minus 1/2. And the only thing I'm doing here is when you integrate that, because capital T, the t bar, I mean, is 4 years. When you integrate this, the 1 over t cancels the t right there. And then you evaluate that between 0 and 2. And what do you get for this? And that should be right. I didn't do this one, but anybody? You got it? No? You got a calculator? Huh? Just 1 minus e to the minus 1.
Yeah, 0.3935.
Is that right? I may not, right? Now, this is the only thing I'm really trying to tell you, these exponential decays, and this happens all the time. It doesn't matter what happened back here. The last known event that says it didn't fail is the point you look at. And if you want the point, the probability it fails between that point and any other point, just take the original thing and use the original curve with a skew out to here, but really just take it and say it starts at 0 and look at this distance and make it that distance. That's the way I do these, and you will not, I may not explain it in exactly a strict mathematical sense, but when I visualize what's going on, that's what I'm doing. And you can write it in terms of all these integrations, but you can get confused with that. This is, in my opinion, much easier to see. All right? Okay. Now, a couple other things I want to say about this. There's a problem. I got 2 books here. I brought my book in from home, and I have one here. If you take a look at problem, hold on for 1 second. Trying to figure out where this problem came from. This is the Rayleigh distribution using conditional probability. You know what's in there? Oh yeah, this is on page 101. And here's what he says. Can you turn to page 101? And go to the second paragraph. And what I want to do is set this up, because this really is kind of a neat, this will show you another problem with this conditional probability, but using a Rayleigh functional form. And I really think it'll help. We can do problems in the back, but there's one particular problem I do want to do before I jump into chapter 3. But so for this one, he says we have a target. This one I remember. And he says the diameter of the target is equal to 12 inches. All right. And then he says that a guy's shooting an arrow at him, and he's shooting at the bullseye. So this is the classic Rayleigh distribution. And you have some distance r measured from the bullseye to the point where the arrow hits. And he's saying that f of x has the same form as f of y, and it has means of 0. So the most likely, it's basically the average value is dead center. Now in there, he gives you, what's the standard deviation? Is it 4 inches?
The second illustration.
Remember the
4 inches.
Nice. So he says the standard deviation, but this is a B's distributions. This is the key. It's not the standard deviation of the Rayleigh, is it?
It's the Gaussian.
Yeah, and that's important. So I would put f of, or sigma of x, and that's 4 inches. With me? Now, based on that, he says, he's asking some questions. He says, if the arrow hits the target, what's the probability of certain events occurring? So the condition is it hit the target. With me? All right, so for this one, the conditional, normally the Rayleigh density, if you think about this, f of r, for Rayleigh density is what? Well, it's r over sigma squared, isn't it? exp to the minus r squared over 2 sigma squared, but that's Rayleigh, that's the Gaussian density function, and then f of r, the cumulative density function, is going to be equal to 1 minus e to the minus r squared over 2 sigma of x squared. And that would be the cumulative distribution function. Do y'all remember that, class? So now, what he wants is the probability, and a Venn diagram is good for this one, but can you tell me the next part? He wants the probability, given the arrow hits the target, so he wants the probability,
Unconditional.
and so hits target of what occurred. Doesn't matter what it is.
I'm still trying to confuse what. So you want the unconditional mean value of missed distance from the center of the target for all attempts, including those that miss the target completely. Then it gives Rayleigh.
I got that.
thing. Okay. Now we seek to find the conditional mean value of the missed distance given that the arrow strikes the target.
Okay. All right. So we want the mean distance given the arrow strikes the target. Now follow me on this. So here I'm going to get f of r, and I think I'm going to need your help on this one. F of r, this is a density function, given it struck the target, or given m, where m is it struck the target. With me? Y'all with me in this class? So take the original density function, that's r over sigma of x squared exp. Then you can put in r squared over 2 sigma of x squared. Now that's like your original f of r right here. And then you divide it by, now it's the event that we have to normalize based on. And I'm using this word, it's kind of loose, but now you have to take a look at what he's saying actually happened. It's not that it basically is within 12-inch diameter or within 6-inch, right? So it's inside there. So now you got to integrate, and this is the easy one, from 0 to 6-inch diameter. And here it's just going to be r. This is going to be a constant. 1 second, I'll show you why. It's going to be exp to the minus r squared over 2 sigma of x squared dr. Well, that itself means this. M is just that it hit the target. I leave the top alone over sigma of x squared exp to the minus r squared over 2 sigma x squared. But this downstairs becomes simply 1 minus exp, and now I'll put the value in. So it's normally the argument is minus r squared over 2 sigma x squared. I'll put the values in. So this is going to be exp to the r. Well, r is 6. Square it. That's going to be 36 over 2 sigma, and that's squared, by the way. What was sigma? 4. So it's 2 times 16, right? And that's just a constant value. Let me slow down. Can you follow me what I'm doing here? I'm trying to normalize this thing or scale it proportionally. So now I'm going to go over there. Oh, boy. And you'll have to help me with this one too. So I have my, this, can you all see it in the class? Can you see this right here? Or do I need to rewrite it? Can you read it? Now I have to integrate that. That's the density function, but I want the expected value of the miss. So I have to multiply that by r. You with me? So now I need to get this, the expected value of how much I'm going to miss by of r. I use capital R. Given that it hit the target, it's going to be an integral from 0 to 6 because that's the radial distance. Call it 6 inches. And then it's going to be r times that, so I get an r squared. And I have to make this one. And then I get exp minus r squared over 2 sigma of x squared. Now, that's really 2 times 16 and 32. I might as well just put 32 in there. dr. I've got that, and I'm going to just show you this. Now, I got sigma x squared there, so I can take divided by 16 here, and then it's divided by this. And I don't know what that is, but it's going to be 1 minus exp to the minus 36 over 32. And I know he does it in the book, but I had to do this integral myself to prove it. So I've got a 1 over 16 can come out in front, but that's an r squared. That type of integration, see if your calculators can do that decent, fairly decent way. So I have 16, 1 minus exp minus 36 over 32. And then I have the integral of r squared, I'll get out of the way in a second, minus r squared over 32 dr from 0 to 6. What do you get for that? That would be the expected value of r.
$1.396.
On the top. I didn't do the bottom.
Okay. 1.396 divided by all this. I don't know what that is. Well, I'll tell you what, just give me, see if it comes out right. You do this one, Ken? What's that? Yeah, here's what you need to do. Do the first integral and store that information. For the entire answer? Well, he has 3.60. I did this one. I believe it comes out right. I mean, I think his answer is right on this.
3.601 inches.
Did you do it, the integration, or just look at?
I just looked, that's what he had in the book.
I know, but
I got 1.129.
all right, could you do me one favor? That last part that he has in there, I believe that's right, because if you take this value right here times 16, you should get 10 point something. So this, just take a look at that
Oh, I
value.
know what I did wrong. I see what I did wrong.
It's
What?
10,
I see what I did wrong.
the bottom there is 10,
10 point.
10.8056.
Yeah, 3 points.
3 points.
10.56, right? Did you say 10.56?
At 3.547.
Believe
He has 10.806.
I got 8056.
Oh, 80. And did you get the right answer then? Or no? I think it's right. 3.54. And he has 3.601. I think I got something like that too. I think it's rounded, but I'm not sure where.
Okay, let's see.
Probably at 10.806.
Huh?
10.806.
Okay, I said I did wrong. Okay, okay, I see what I did wrong. Okay.
So I want to tell you, the reason,
16 says
part of the reason I'm doing this right here is because this is the kind of mistakes you're going to make on quizzes. You're going to have a right idea, but calculating the integral correctly will be a mistake.
Okay. I got
What
that.
did you do wrong, by the way?
I put 16 instead of 32 when you're in the exponent. You're still wrong.
Yeah, it's stupid things. All right. Now, if you look at the problems in section 8 and 9, these are just applications. It's the same basic stuff. I'm going to take one look at this thing. I have to tell you that I don't think I assigned any section 9 problems, right? 2 dash. What you're going to see is some of these get discrete. Well, here, remember how we had, when we talked about the binomial coefficients and stuff like that, the value, you may have to use those for some of these, at least I said. So if you look at 2-8, just do me one favor. For this one, the first one, it says think about what I'm saying. This is 2-8.1, problem in the back. For a communication satellite system, in problem 2.73, you don't have to worry. It's got a mean time to failure 6 years, and that's all it's saying. Find the conditional probability that the satellite will survive 10 years or more, given that it has survived 5 years. Can you all follow me? Can you hear me on this? So the only thing that matters in there, you got the mean time to failure at 6 years. What's the probability it will survive 10 years, given it has survived 5 years? Just tell me.
You do the bounds from 5 to 10. Shift over
Just
here.
0 to 5, right?
0 to 5.
Just take the, right? So it's really 1 minus exp to the minus, and it would be 5 over 4, right? Y'all follow me? That's all you do with that one. Find the conditional mean lifetime of the system given that it has survived for 3 years. Now this is one just makes you think. Well, what is the mean of when you have something with a mean time to failure of 4 years? The mean time to failure is 4 years. They give you the mean, right? Well, what if it survives 3 years? What do you think the mean time is going to be?
It's going to be
3 plus 4, right? Just shift over the mean value. Can you follow me on that, class? Did you remember doing these kind of problems? These are the easy ones that people mess up. I promise you they do, because they'll do that integration in some crazy way. You don't need to. And then he goes into 2-7.1. Why don't we do 2-7.1? And then we'll do 2-8.2 if we have to. Wait a second.
2.71 in the back.
In the chapter. I want to do this one anyway. I don't think I did this one. It's an actual very good problem. I believe it's a good problem. Hold on for 1 second. I'm trying to make sure that what I see is, I call them tricks. But some of the insight that I have just doing these things in all sorts of ways and all sorts of applications, I don't try to make it more complicated than it is. I visualize a lot of it. So this is 2-7.1 in the chapter. I want to get that up there quick, and then we'll talk about the others. This one was assigned. Do you remember this class? 2-7.1, and has a random variable x, right?
Mhm.
And that is equal to x is equal to cosine of theta, right? And then he says theta is distributed from either 0 to 2 pi, or it could be minus pi to pi because it's got a constant density. With me? I'm going to go from minus pi to pi, but it doesn't matter really. Minus pi to pi. And this is f of theta. So just a quick question. What's the height right here?
1 over 2 pi.
The area's got to be 1, right? Width is 2 pi, height is 1 over 2 pi. So this is just 1 over 2 pi between that range. Agreed, class? Now, the way he does, I'm going to do this. So now he's going to say he wants, this is the density function for theta, this is the relationship. He wants f of x, right? So, and I'll try to say, I was messing with this. I was trying to figure out the easiest way to do this. So if you look at this, well, if I want f of x, really, or better yet, let's do it this way. F of x, right, random variable x less than x, is the same thing as, really, f of, and it would be this cosine of theta less than or equal to x. Y'all follow me? So what is that? Well, if I look at this, when I think about a cosine function, if I was to plot it on top of here, it would look like this. If that goes to pi, cosine function does this. This is one of the reasons I did it from minus pi to pi. Can you all follow me on this? Yeah, this blue line is cosine of theta. Okay. Now, if you look at that for a second, the probability of the cosine theta being less than x. So this would be, say, x, which is equal to cosine of theta. There are 2 points, right, that I have to worry about. For less than that, and he says less than that, right? Can you all follow me? My reasoning on this one? It's the probability one. That it's, or I should say it's 1 minus the probability that it's from here to here, right? Agree, class? So I can say that really this is equal to the probability of x magnitude being less than, or I should say, cosine. No, I can do it. I can write the integral. So it's going to be 1 minus, and this would be, think about this. I have 2 points, so I'm going to have this point right here would be minus the inverse cosine, a cosine of x, and this point would be plus a cosine, a cosine of x. A is just an inverse. Y'all agree with me? I need the inverse cosine because if I'm given x, I need theta to do this one, right? So it's going to be 1 minus, and technically it would be the integral from minus a cosine of x to a cosine of x of 1 over 2 pi d theta. Y'all agree with that? Take them all. I just put the density. What I really need is, I got to find the probabilities between here and here, and I got to take that probability and subtract it from 1 to find the probability that it's less than that. Agreed, class? If you look at this, that's an even function, so I can just say it's this, and I can go from 0 to that point and multiply by 2. Can you all follow me? You with me? Now, I'm going to erase the 2 here and the 2 here, just to make my life easier, right? And then I'm going to come over here. So now I say, how many did this problem? I'm doing it different, but I think it's easy. So now if you take a look at f of x, equal to, I'm putting the whole thing in here, 1 minus, and it's going to be 1 over pi, integral from 0 to inverse cosine d theta. And if I want f of x then simply becomes the derivative of the capital F of x less than x with respect to x. And that is interesting because it's 1 minus 1 over pi here. And then when you integrate this thing, it's just a cosine of x, right? So now I need the derivative with respect to x of a cosine of x. Right? And you can look this up if you want. But I think this is easier to do it this way. If I look at that, and I don't know how he does it in the book. If I have x equal to the cosine of theta, then dx d theta is equal to sine theta, right? Correct? And that should be, that's going to be a minus 1 over square root business, but I'm trying to figure out how I actually did this earlier. When I took a look at this, if this is theta, and this is x, this is y, and this is square root of x squared plus y squared. When I look at this, cosine of theta is equal to x over the square root of x squared plus y squared. As such, it's not occurring to me the easy way to get this, but this is going to end up being a derivative of a cosine, and that's going to be a minus. So this is minus 1 over pi, and then the derivative of this one is going to give you another minus 1 over the square root of x squared plus 1, where x is the cosine. I know that's how it comes out in that. Y'all remember doing this at all? I'm trying to think of, I didn't mess with this last night, but I've done this one. There's a nifty trick, but I forgot exactly what it is. Hold on. See if I got this right. Oh, Well, this is gonna be the answer to that one. That should be the density function. You remember? I don't know if that's correct, but I think it is.
Yeah.
All right. But the way you get it is you have to take the derivative of a cosine. There's a trick to this one. I'm trying to think of what it is. If I define a cosine, oh, I think it's that. If that's cosine. Inverse cosine would be. Anyway, that should be the value. Then he asked for what? The probability of something occurring?
You wanted the mean value x.
Okay. Now, I'm going to show you something about that. This density function right here is constant, right? So if you look at this, I think you know this. If I want the mean value of x, that's the expected value of cosine of theta, right? Over its range from either 0 to 2 pi or from minus pi to pi. What is that going to have to be?
0.
It has to be 0 by definition, right? And then he asked for what?
Variance with x.
Now, the mean value is 0, right? So if we find mean squared value, right, we have, how do you get the expected value of x? Well, the expected value of x squared would be equal to the expected value of cosine squared of theta, right? It's uniformly distributed. Do you remember the half angle formulas? That is the expected value, or the way you break these things up in what? 1/2, right? And it's going to be plus cosine of 2 theta over 2. Do you all remember doing something like that? Now, if you look at this, what's the expected value of any kind of a trig function, sine or cosine, over a full period, always? 0. This goes away, it's 1/2. I think the answer is 1/2. That part, though, there's a trick to that, and it's bugging me, but I can't think of it right now. Now, next thing I want to tell you is in chapter 3, in 2A2, might as well just finish my thought here. For equation 2-8.2, for the random variable x in problem 2-7.1, that's the one we just did, find the conditional probability density of x given m, where m is the event from 0 to pi over 2. Now, here's the only thing you have to do. Take f of x and just divide it by the area from 0 to pi over 2, which is a quarter. Are you with me? That's it. I'll give you some more. You're going to see most of these problems, if you actually take a look, they'll become fairly obvious based on what I'm talking about, normalizing with respect to the area. That's the way I think of that. All right, the next section that I did want to mention, just about out of time, but if we take a look into the next conditional probability of 2 or more variables, I know I'm out of time just about, but here's what happens. Now we don't have f of x. We have an f of x comma y. That's called a joint density function. So there's PowerPoints I put up there. I'm going to give you some reading and stuff. And I know we have a long time before we need it, but I did want to get this out there today. So now we're going to have the density function f of x, y, no longer just one variable. That means we really have something, it's hard to understand this. This is the x-axis and this is the y-axis. And we look at f of x, y, we can think of it as a surface. Now the density function has to be strict positive. It has to be from 0 or positive. Can't have negative values. So it's a surface, really, right? It's some kind of a surface, you might say, that is going to be like in a 2-dimensional plane. You all with me, class? It's really a 3-dimensional view you'd want. So if I want the probability of the random variable x between some x1 and less than or equal to some x2, and the probability that random variable y is greater than y1, less than y2, then it really is taking this and integrating over the surface that defines. And the way I did it would be a square region, right? It would be something like from here to here, here to here, and it would be, say square region, but it's going to be a surface right here. If you think about that surface. Following? Now, in his book, or in the notes I posted those slides, right? And I'll give you the problems and the solutions, but he gives you, more or less just extends what we did before with finding the moments. And if you did conditional probabilities, and if we had a joint density function f of xy, we wanted f of x, we'd integrate out y. Take the density function f of x comma y, put it times dy, integrate from y is minus infinity to infinity. Now we get just f of x. A lot of this stuff is intuitive. The problems, the tricky stuff is when we have an x and a y, but there's a functional form, x is y squared, or x is y cubed. Now I want the probability of like y being less than 3, and then that's what's coming up. I'll give you some more on this. I didn't run out of time, but this is a good stopping point. We're going to start in the next chapter. And when we get back, let's discuss when you want your test. So on a Wednesday, is that fair, kid? You're going to be back, right? You're going to Texas, right?
Test on Wednesday. We come back on Wednesday.
We talk about when we're going to have our
Okay.
Because I'm going to let you guys vote on it, but I want to take care of that next.
Yeah. Tomorrow.
How'd you guys doing your thermo?
High.
All right.
Average is high.
Great. Thermo was not a class that I wish I was more attentive when I took it as an